Welcome back. So this is the second in the series of videos looking at the atomic structure. In this video, we're just going to be looking at the structure of the elements and the atoms. So as you're well aware, there are well over 100 elements. Some of those are natural and some of those are man-made. In chemistry, we're basically interested in the 92 naturally occurring elements. But first of all, we need to define what is an element. So one of the simplest ways of thinking about an element is that it is one type of atom. It's one easy way to think of an element. Another way of thinking about it is it's the simplest chemical substance which cannot be decomposed by either chemical means or via electricity. So you can't break it down into anything which is chemically simpler, and it only contains this one type of atom. As we said in the previous video, you need to know the symbols for the first 30. Now, a very simple picture of an atom looks like this. We have a nucleus where the protons and the neutrons sit, and we have these things which we call shells where we find the electrons. Obviously, it's not quite this simple, okay, but for this exercise, it's a good enough model. So this atom here is an example of an atom of lithium. Now the reason I know that is because of these, the protons. So this atom has 3 protons in its nucleus, and that's what makes it a lithium atom. I can change the number of electrons. I can either remove or add electrons. I can remove or add neutrons, and it would still be lithium. It is the proton number that determines which element we have present. So how do I know that this is an atom of lithium? Because it has 3 protons in its nucleus. So changing the number of neutrons or electrons does not change the element. The element is determined by the number of protons. So I'd like you to use your periodic table and find the names of these elements. So there you have the completed table. It's just a simple job of looking up the number of protons, and that will give you the element. So where the number of protons equals the number of electrons, you have a neutral atom. However, if you change the number of electrons, remember you're not going to change the element, you're just going to change it from an atom into an ion. So an ion is an atom, or it could be a group of atoms, if it's a polyatomic, that have gained or lost electrons. Notice to make an ion, you never gain or lose protons. You only ever gain or lose electrons. Remember, if you change the proton number, you're actually going to change the whole element. And we're not doing that here, we're just making an ion. So again, I'd like you to pause the video and have a go at the table at the bottom of page 8. So there you have the completed table. The number of protons, that gives us the symbol, because remember the proton number gives us the element. And then if there's the same number of protons and electrons, we get the neutral atom. However, if there are less electrons than protons, we'll get a positive charge. If there are more electrons than protons, we'll get a negative charge. And do notice that some things, for example nitrogen here, could be -3 or it could be +3. So you have different charges dependent on the ratios of the protons to electrons. So we're now looking at page 9, and we're just going to look for a second at the things that make up are atoms, and they are protons, neutrons, and electrons. So the proton has a charge of 1. The electron also has a charge of 1, but it's a -1. And the neutron is neutral, so it has 0 charge. Now, in terms of mass, we say the proton has a mass of 1, as does the neutron. The electron, which is much, much smaller than the proton or neutron, we say it has a mass of approximately 1/2000th of the mass of a proton. To be exact, it's 1836th of the mass of a proton, but 1/2000th of the mass is absolutely fine. Okay? So again, a few more definitions for you to know. The mass number of an isotope is the number of protons plus neutrons in the nucleus of an atom, whereas the atomic number is the number just of the protons in the nucleus of an atom. So when you look on your periodic table, you're going to see two numbers. You're going to see the mass number and the atomic number. And the larger of these numbers is always the mass number, because it's the number of protons plus the number of neutrons, and the atomic number is a smaller number because it's just the number of protons. So we can use these numbers for elements to work out the number of protons, neutrons, and electrons. So for example, if we look here for sodium, sodium has an atomic number of 11, and that is therefore the number of protons. Because it's a neutral atom, it is also the number of electrons. 23, on the other hand, is the mass number. So that is the number of protons plus neutrons. Well, if I have 11 protons, and I know that protons plus neutrons equals the mass number, I must have 12 neutrons. So have a go at completing the rest of that table. Okay, so there you can see the completed table of all the elements, all the atoms. Okay, so do notice these are all single atoms, and they are all actually also single isotopes. So this introduces us to a very important concept, isotopes. Now hopefully you've come across these at GCSE, but just to remind you of them. Isotopes are atoms of the same element, which have the same number of protons, that's why they're the same element in the nucleus, but a different number of neutrons. So the atomic number is going to be the same, but the mass number is going to be different. So for example, we've got isotopes of chlorine. So chlorine has two isotopes. They are chlorine 35 and chlorine 37. So they're both chlorine because they have the same number of protons in the nucleus, but they have a different number of neutrons, so they will have a different mass number. To understand this next section, we need to get an idea about what we mean by mass. Now, the standard international unit for mass, the SI unit, is the kilogram. And up until 2019, the kilogram was defined as a ball of metal sitting in a vault somewhere outside of Paris. But there was a problem with this. It was the last SI unit to be based on a physical object. All the other SI units had been moved so that they were related to an underlying physical constant. So, for example, the speed of light. But the kilogram was the last SI unit which was defined by a physical object. So in 2019, the unit of the kilogram was changed. So this is now how the kilogram is defined. Obviously, it's a lot harder and more complex than a big ball of metal sitting in a vault somewhere outside of Paris, but because it's moved away from a physical object, it's much easier to email a formula to somebody rather than having everybody come and measuring their standard kilograms against the international prototype. It also underlines the importance in science of having defined terms so that we all agree with what we're talking about. So this is an internationally agreed version of the kilogram, and everybody can make sure that they're talking about the same thing, that when we say that this weighs exactly 1 kilogram, that's the same wherever you are in the world. So the relative isotopic mass is the mass of one atom of an isotope relative to 1/12 the mass of an atom of the isotope carbon-12. So it's very important, again, in chemistry that we define what we are talking about so we can all agree that we're talking about the same thing. And we use carbon-12 isotope as our standard unit. And then we compare things to that. So if I've got an atom of hydrogen, the isotope hydrogen-1, it would be exactly 1/12 the mass of the atom of carbon-12. So here we have some isotopes of chlorine and some isotopes of neon. So they both have the same number of protons because they're both chlorine. They both have the same number of electrons because they're atoms, not ions, and they both have the same atomic number because they're same element. It is the number of neutrons which is different. So in terms of the isotope chlorine-35, it has 18 neutrons in the nucleus, whereas chlorine-37 has 20. So you can repeat the same exercise for neon. And you get the idea. Same number of protons, electrons, and atomic number. And then my neutron number is my proton number plus my neutron number. So neon 20 has 20 neutrons in its nucleus, but neon 22 has 12 neutrons in its nucleus. So in chemistry, we use this idea of a relative atomic mass. So relative just means compared to something else. Originally, we compared everything to hydrogen because it was the lightest element, but it was very difficult to produce pure samples of hydrogen without any hydrogen isotopes. So we tend nowadays to use a single isotope, which is very easy to get a very pure sample of that, and that is carbon-12. So everything nowadays is compared to carbon-12. So the relative atomic mass is the average mass, and sometimes it's called the weighted average mass, of an atom of an element relative to 1/12 the mass of an atom of the isotope carbon-12. So we take carbon-12 as our fixed point and we compare everything to that. It's a little bit like we used to do with the kilogram, standard kilogram, and we compared everything to that. So the relative molecular mass we can now work out. We've got formulas for our molecules like C6H12. We know this contains 6 carbon atoms and 12 hydrogen atoms. Well, I know what the mass of one carbon atom is, and I know what the mass of one hydrogen atom is, so I can work this out by using my periodic table. So I've got 6 lots of carbon atoms, and each carbon atom weighs 12, and I've got 12 hydrogen atoms, each of which weighs 1. So I'm going to use my calculator now to work that out. So I've got 6 lots of carbon-12 and 12 lots of hydrogen. So in total, that gives me an RMM of 84. And this is the mass of 1 mole of it. So the units for RMM are grams per mole. Okay, and you're going to do a lot more of this when you study moles in a moles 1 pack. Having go to the next one, CH2F2. So I've got 1 carbon, 2 hydrogens and 2 fluorines. So I have 1 carbon, which is 12, I have 2 lots of hydrogens, and I have 2 lots of fluorine. And for the last one, I've got H2SO4. I've got 2 lots of hydrogen, I've got 1 sulfur. Notice sulfur on your periodic table has the mass 32.1. Why it's a decimal I'll come back to later. And 4 oxygens. And if we add those all together, we get the RMN. So I've worked those out here. So that's 52 grams per mole. Notice I've written it in this standard form, grams mole to the -1. Here again I've added those numbers up and I've got 98.1 grams per mole. So that is telling me that 1 mole of H2SO4 weighs 98.1 grams. We can also use this to work out the relative formula mass for giant structures. So here I don't have a fixed number of species because I've got a giant lattice, but I can still work out the mass of 1 mole of it by looking at the ratio of the ions. So there we have the formula mass for calcium hydroxide, magnesium chloride and sodium nitrate. And you can see there the workings out and giving you the RMM, 74.1 grams per mole and so on. So you're going to practice a lot more of these when you look at moles. Okay, so that finishes this section of the notes looking at the atom. In the next section of the notes, we're going to be going on to look at mass spectroscopy. Hopefully, nothing up to this point has been new to you. But as we move into mass spectroscopy, we will be coming across concepts that you've not come across before. So I suggest you have a look at the PowerPoint before you have a look at the video, and then we'll go through the video with the pack together. So until then, take care, stay safe, see you soon, bye bye.